So in this video, we're going to go over the 20 practice questions in the Practice Chapter 3 chapter module. So let's look at question number 1. So here, there's some background information about PKU, and what's really important is that we need to know is the recessive trait. So the question here is actually, what is the probability that two heterozygous parents have a PKU child, a heterozygous child, and a homozygous non-PKU child? So here we have two parents, they're heterozygous, so that's going to be A, lowercase a. So it really doesn't matter what letters I choose here. Here I just chose A because that's the simplest. So both parents are going to be this genotype right here. So this is a straightforward Punnett square. So we're going to have heterozygote genotypes on the outside. And our square is going to look something like this. Okay, so question A, or part A, is asking you what the probability is that we'll have a PKU child. So it's a recessive trait, so you need two recessive alleles to have a PKU child. So here, that's 25%. Next, it asks for heterozygous childs. So we have two of those, so 2 out of 4, so 50%. And then a homozygous non-PKU child. So when they say homozygous non-PKU, they essentially mean homozygous dominant. So that's 1 out of 4, so 25%. So a pretty straightforward question. Let's erase this. Okay, question 2. So unattached earlobes are inherited as a dominant trait. Attached earlobes are a recessive trait. So essentially, to have attached earlobes, we would need 2 lowercase a's. For unattached earlobes, that's a lowercase a, so heterozygote, or you can have 2 uppercase a's. So unattached earlobes is inherited as a dominant trait. So as long as you have 1 uppercase a allele, you're going to have unattached earlobes. The only instance where you're going to have attached earlobes is, again, if you have 2 lowercase a's, so you're homozygous recessive. So suppose a homozygous man with unattached earlobes, that would mean a uppercase a, so 2 uppercase a's, so homozygous dominant, marries a homozygous woman who has attached earlobes. So essentially that's lowercase a, lowercase a. So what type of earlobes will their children have? So let's do the cross for that. So the man's uppercase a, so homozygous dominant. The female's homozygous recessive. And really there's only one possibility here. So they're all going to be heterozygous. At least their children will be. So again, since we have 1 uppercase A allele, this means all their children are going to be or have unattached earlobes. Okay, so that solves part A. Part B, if these children marry someone with the same genotype as themselves, will all their children have attached earlobes? So let's do that cross. So we know all their children are going to have or be heterozygous. Let's go to a new page. So here we're just going to cross heterozygous children with another heterozygous person. Let's go back to the question. So will all their children have attached earlobes? No. So here we have somebody with unattached earlobes. Or sorry, attached earlobes. So 75% unattached and 25% attached. So again, question B says if they marry somebody with the same genotype as themselves, will all those children have attached earlobes? So again, the answer is no. So 75% will have unattached, and only 25% will have attached earlobes. Let's clear this off. Okay, question 3. In shorthorn cattle, a red animal is crossed with a white animal, and this gives all roan in F1 generation. So roan, I think, is a tannish, brownish color. So essentially, this question right here is an incomplete dominance question. So essentially, the roan is sort of an intermediate between red and white. So the question is, give the genotypic and phenotypic ratio that will result from crossing roan offspring of the F1 generation. So essentially, you can imagine the red animal would be uppercase A, the white animal would be lowercase a, lowercase a. And again, if this is a codominant question, or sorry, not codominant, incomplete dominance question, all of their offspring are going to be heterozygous. So that would give 100% roan, or essentially 100% of the intermediate phenotype. So essentially, you'll get the same cross as we did with the previous question. So if you cross those roan animals, which are essentially heterozygous, you're going to get 75%. So since this is an incomplete dominance, it messes with the ratios. So you're going to have 25% red, 25% white, and now you're going to have 50% roan. So again, since this is incomplete dominance, the heterozygotes have their own unique phenotype. So that's 50% of those heterozygotes, or 50% of the offspring, are going to be roan, 25% will be red, and 25% will be white. So it's the same cross, but the phenotypic ratios are going to be different because it's an incomplete dominance question. So slightly different from question 2. Okay, so questions 4 and 5. In horses, black coat is B. That's dominant to a brown coat. And being a trotter, T is dominant to being a pacer. Okay, so a black pacer. So for black coat color, we don't know if it is heterozygous or homozygous dominant. So we're going to put B question mark there. We'll come back to that later. They are a pacer though. So we know a pacer must have two lowercase t's. Since being a pacer is a recessive trait, you need two lowercase t's there. So it's B question mark two lowercase t's since they're a pacer. Just like pacer for a brown coat, that's recessive, so we know two lowercase b's. Here they're a trotter though, so we know they have at least one uppercase T. We don't know about the second allele there. The offspring though is a brown pacer. Okay. So since they're brown, we know they have two lowercase b's. Again, brown is recessive. You need two lowercase b's to have brown. Being a pacer is also recessive, so they are two lowercase t's. Okay, so let's find out how this offspring got all these alleles. So you know at least one of those b's came from the brown trotter. You know at least one of those lowercase t's came from this black pacer. Okay, so now we don't know where these two alleles came from. So those two alleles didn't show up automatically. they must have been found in the black pacer and in the brown trotter. So the brown trotter gave one of its lowercase b alleles, the black pacer definitely gave one of their lowercase t alleles. It's from this logic, so we know that we got a second lowercase b and a second lowercase t from somewhere. So it must have been from the other parent, so that means the other parent must have been a carrier for these recessive alleles. So that's sort of the logic you have to use here. It's a little bit of a logic puzzle with some of these questions. But if you understand inheritance, then that should have made sense. So question 5. A black pacer is mated to a brown trotter. So pacer again, let's just label the phenotypes or the genotypes we know. So that's lowercase t, and then we have a brown trotter, so lowercase b, and produces a black trotter offspring. So really the question then is we're trying to figure out where the black, or what the genotype of the black pacer is, what the genotype of the brown trotter is. So trotter again, there's at least one uppercase T. We don't know about the second allele. For the black pacer, you know they have two lowercase t's, but for the B allele, we don't know what their second B allele is. Okay, but we know we produce a black trotter offspring. So that means they have at least one uppercase B allele, and trotter, so they have at least one uppercase T. It's question mark there. So for this question, it's kind of ambiguous. So it's not going to be super clear what the answer is, which is why it says give all possible genotypes for the offspring. So here it could be BB, TT, maybe B, B, T, and T. So really we don't know from this question what exactly their genotype is. But I believe these are all the possibilities there, since we don't know what the genotypes of the parents are just from this question alone. So this question is sort of an ambiguous version of question number 4. So question 4 was very clear in what the genotypes were, so you can figure that out. Okay, so question 6 looks up blood type. So blood type is a codominant trait. So if you don't know what that is, if you go to the earlier parts of this packet here, it talks all about various blood types. And very importantly, the genotypes that go along with each. Okay, so if a child's blood type is A, and the mother's blood type is O, so O is I, what blood types might the father have? So we know the child's blood type is A, so it's either I, A, lowercase I, or I, A. So essentially those are the two possibilities here. However, we know the mother has two lowercase i's, and she's type O. So you know the child must have at least one lowercase I. So we know the child must have that genotype right there. The mother has two lowercase i's, so at least the child must have one of those. So this means the I uppercase A, so the A blood type must have come from the father. So we know the father must have had at least one uppercase A. So the blood type of the father must be A blood type. However, we don't know if the father's I uppercase A I or lowercase I, or if the father has homozygous A alleles there. So both of these are possible for the genotypes of the father. Okay, so question 7. So this looks like a long one. So both Miss Smith and Mr. Jones had a baby girl the same day in the hospital. Miss Smith took the baby home, which is called Shirley. Essentially, they have a switched baby. So Mr. Smith is type A, Miss Smith is type B. Mr. Jones is type A, and Miss Jones is type A, Shirley is type O. Okay, so let's start organizing the information in this. Okay, so Smith, so Mr. Smith, Miss Smith, so we know Mr. Smith is type A, Miss Smith is type B. And their daughter, so Miss Smith, so Miss Smith has Shirley, and Shirley is type O. Okay, and Mr. Jones is type A, and Miss Jones is type A. And it looks like their daughter's name is Jane, and Jane is type B. Okay, so looking at this, there's absolutely no way that Jane is Mr. and Mrs. Jones' daughter. So this B phenotype won't show up here. So remember, blood type is co-dominant. So if any of these people had a B allele, so if Mr. Jones or Miss Jones had a B allele, it would absolutely show up in their blood type. So it would be blood type AB if they had a B allele. So the B allele is not going to show up spontaneously, so Jane is not their daughter. Okay, so question 8. Looks like another blood type question. So here we're just doing actually a simple Punnett square. So I uppercase A, I. And then AB blood type. So essentially when you have alleles that have this superscript text right there, you just fill in the table just like you fill in any Punnett square. So you just write the letters, so you have I uppercase A, like that. So exactly the same as you always do it. Let's go back to the worksheet to see what the question is. So what are the possible blood types that their children could have? So here, top left, we can have A. So two uppercase A's, or I should say two I uppercase A's. It's the same blood type as I uppercase A, lowercase I. So still, both of these top ones are going to give A blood type. The second possibility is AB. So remember, it's codominant. So we're going to get both the A blood type and the B blood type. And the last one then is B. So here we just have the B allele and then a lowercase I. So the possible blood types are A, AB, and B. So question 9. So a white guinea pig whose parents were black is crossed with a black guinea pig whose male parent was white and whose female parent was black. Two white offspring result. Determine genotypes of all individuals mentioned. About which individual is there some doubt. So it's not implied here, but I believe the white guinea pig, or the white trait, is recessive. The black trait is dominant. So we know this white guinea pig with two recessive alleles had parents who were black. Okay. So if both parents are black, that means they each had one uppercase, whoops, wrong letter. These had one lowercase a allele. So each of them had one lowercase a allele. But we know they were black. So if they were black, that means they have at least one uppercase a allele. So the parents essentially were heterozygous. So each parent gave one of these lowercase a alleles, and we know they have one uppercase a allele each. So one dominant allele each since they were black. If one of them had two uppercase alleles, or they were homozygous dominant, it would not be possible to get a white guinea pig. So we know the parents were heterozygous. So that white guinea pig is then crossed with a black guinea pig, whose male parent was white and whose female parent was black. So this black guinea pig, we know he has at least one uppercase A allele. One of the parents is white, though. So we know the white is two lowercase a alleles. So we know this black guinea pig got a lowercase a allele. So a black guinea pig must be heterozygous. Again, they have to take an allele from their white parent, so they must have at least one recessive allele. And the female parent was black. So just off the cuff, I don't think there's anything we can say about this other than they have at least one uppercase A allele. So we don't know more about them. Two white offspring result. So that means lowercase a, lowercase a. So we already done the question, determine the genotypes of all the individuals mentioned, and then about what individuals are summed out. So that is the female black parent. So this parent right here of the black guinea pig. So we're not sure if they're homozygous dominant or if they're heterozygous. At least off the top of my head, I cannot tell from this question. Okay, so 10 looks like a similar question. So heterozygous black guinea pig. Let's write the genotypes. This means each of homozygous recessive white guinea pig. Lowercase a, lowercase a. Predict the genotypic and phenotypic ratios expressed or expected from crossing the F1 progeny. Okay, so let's do the first cross. So we heterozygous with homozygous recessive. Let's do the Punnett square. Okay, this looks like 50-50. Black versus white. And 50-50 heterozygous. Okay. Here, though, it looks like it wants us to get the genotypic and phenotypic ratios of the F1 progeny. And here it looks like we're crossing them back to the black parent and then to the white parent. So here this makes the question a little bit more trickier. Or maybe not trickier, it's the correct word, but more elaborate or time-consuming. So we saw the offspring were either homozygous recessive or they were homozygous or heterozygous. So heterozygous or homozygous recessive. So we just have to take each of those and cross them back to their parents. So we're going to have quite a few Punnett squares there. So we're going to have 2, 4, so 4 Punnett squares in total. But the question here is pretty straightforward, just finding out what the genotypic and phenotypic ratios are. Okay, so in humans, freckles is dominant over no freckles. It's just filling out the genotypes. So if you are homozygous recessive, you have no freckles. If you're heterozygous or homozygous dominant, you have freckles. So man is married, or a man with freckles is married to one with freckles as well. But the children have no freckles. Okay, so children have no freckles. So A, lowercase a, and we know each of those had to come from one parent. So one came from dad, and one came from mom. We know that both of them have freckles, so that means they are heterozygous. So both of these parents were carriers. And now we want to figure out what the chance is that each child was going to have freckles. So we're just going to do the cross there. Squeeze into the corner of this paper. So really there was only a 25% chance of having no freckles. So each time they have a child, there's a 25% chance that that child is going to have no freckles. Okay, so 2 persons with sickle cell traits marrying and want to have children, but they're concerned about them having sickle cell anemia. Okay, so this relates to some information that was provided earlier in this packet talking about sickle cell anemia. So it looks like both parents have the sickle cell trait, so they both have that genotype right there. Let's double check that, read the question again. Yes. So it looks like the uppercase A allele is normal, and then this S allele means they have the sickle cell trait. So the 2 lowercase are essentially just 2 S alleles to have sickle cell anemia. Okay, so it looks like we have 50% sickle cell trait carriers, one healthy child, and then one, or essentially 25% chance of having a child with sickle cell anemia. And that answers the question. So what's the probability of their child having sickle cell anemia? That's 25%. And what proportion of the children would we expect to be carriers? So that's 50%. So a pretty straightforward question, as long as you read this information right here. Okay, so if a person with sickle cell trait marries a person, marries a person with normal hemoglobin, so this is going to be HbA, HbA, and the sickle cell trait is going to be HbA, HbS. What's the probability they will have a child with sickle cell anemia? What proportion of their children would you expect to be carriers? So since one of the people has normal hemoglobin, so they have the A alleles, there's a 0% chance that any of their children will have sickle cell anemia. So for that, I don't even need to do Punnett square. That, as long as I know how inheritance works, I know that there's a 0% chance that any of them will have sickle cell anemia. For the carriers, though, that's a little trickier. So for that, let's actually do Punnett square. So one of the parents had normal hemoglobin, so that's HbA, and one of them was a carrier. So do Punnett square. So again, none of these children are HbS, which is a sickle cell anemia genotype. So 50% of these will be carriers, and 50% will be healthy. So again, for the first part of that question about what's the probability that your child will have sickle cell anemia, I didn't need to do a Punnett square for that. You can just do that in your head. But what proportion of the children would you expect to be carriers? It's going to be 50%. So for that, I had to do a Punnett square. So question 14. So for this, it's trying to trick you to do a Punnett square, something crazy like that. Here, the probability is always 50%. So regardless of what happens in the past, even if they had 1 million children, the next child, the probability of them being male or female is always 50%. So it's kind of a trap to make you think about doing a Punnett square, something like that. But if you didn't want to do a Punnett square, just look like this. So the female would be XX, and the male would be XY. XX, XX, XY, XY. So again, 50% probability, regardless of their family history. Okay, so let's look at hemophilia. So hemophilia is an X-linked disease. So it's inherited on the X chromosome. So you have a carrier female. So they are X uppercase A, X lowercase a. So they carry, or I should say, hemophilia is an X-linked recessive disease. It's important to mention that. X-linked recessive. So if they're a carrier, they have one recessive allele. There's no such thing as a carrier male. If a male, since males only have one X chromosome, if they're a carrier, that means they have the disease. So they'll show the phenotype. So they're not technically a carrier. So here they're marrying a normal male. So if it's normal, he must have the uppercase A allele, so he doesn't have a disease. There's nothing on his Y allele. Again, it's X-linked recessive, only on the X chromosome. So here's X uppercase A. So what is the possibility that your son will have the disease? Okay, let's do the Punnett square. Just like all the other Punnett squares with superscript letters, it works exactly the same way as a normal Punnett square. So just X uppercase A, X uppercase A, X uppercase A, X lowercase a, X uppercase A, Y, and X lowercase a, Y. Okay. So what is the probability her sons will have a disease? So we're going to ignore the females. We're going to look at the sons. So of the two possible male genotypes, one is unaffected, so one doesn't have a hemophilia since they have the uppercase A allele, and one is affected, so they do have hemophilia. So that is 50% of the males affected. Okay, so let's look at the daughters. It's impossible for any daughters to be hemophilic, so ignore that I crossed it out. So no. So here they have two uppercase A alleles, and here for the heterozygous or carrier daughter, she is a carrier. Again, she has one uppercase or dominant allele protecting her from hemophilia. So then no, none will be hemophilia or hemophiliacs. But yes, one will be a daughter, or one will be a carrier. And the information about hemophilia being X-linked recessive disease was on the first few pages of this packet. Where's the rest of this as well? Okay, so short hair is due to a dominant gene in rabbits, and long hair is due to a recessive allele. Okay, cross between a short-haired female and a long-haired male produce a litter of 1 long-haired and 7 short-haired bunnies. What are the genotypes of the parents? What phenotypic ratio was expected in the offspring generation? How many of the 8 bunnies were expected to be long-haired? Okay, so this looks like just a probability question. So a cross between a short-haired female. So short hair in this case is the dominant trait. So she could be S, lowercase s, or big S, big S. So since it looks like they were able to produce a long-haired rabbit, which is recessive, so she must be heterozygous. Since there's no way for that long-haired offspring to get two lowercase a, or in this case two lowercase s alleles. So here they chose really bad letters, but these are going to be lowercase s's. So there's no way for that long-haired offspring to get two lowercase s's unless their male or their female or mother was heterozygous. And then the long-haired male, since that's a recessive trait, we know something about him already. So it's going to be lowercase s, lowercase s. Okay, so let's do that cross. So we know the mother is heterozygous, and we know the father is homozygous recessive. So here we were expecting 50% long hair, 50% short. So it looks like their offspring are a little bit different from what we were expecting. They got 1 long hair and 7 short haired. So I already figured out the genotypes of the parent from the question. What is the phenotype ratio that's expected? So we were expecting 4 long-haired and 4 short-haired, but that's not what we got. So really, it's just a probability question. Again, we can use logic to figure out what the parents were. So again, we knew with the child, we knew the long-haired child had 2 lowercase or was homozygous recessive, and from that we knew that the mother had to be a carrier, or else there was just going to be no way we get 2 lowercase or 2 homozygous recessive alleles there. Okay, 17. A dominant gene H produces a wire-haired texture in dogs. Its recessive allele H produces smooth hair. 2 heterozygous wire-haired individuals were crossed and their F1 progeny test crossed. Determine the expected genotype and phenotypic ratios among the test crossed progeny. Then give some notes about what a test crossed is. Okay. So here this question isn't super clear, but it looks like we're crossing 2 heterozygous parents to produce an F1 progeny. Let's do that first. Okay. And then a test cross, as it says, is where we cross a homozygous recessive individual back to each of these. So you would do that cross, and then that cross right there. I was going to do a few Punnett squares for this question. So assuming you didn't know what the genotypes of these individuals were right here, you could do a test cross with this homozygous recessive individual and figure out what offspring phenotypes ratios make sense there. So that's really the point of a test cross, is to identify individuals of unknown genotype. So by crossing back, or crossing this homozygous recessive person or offspring back to the F1 progeny, you can figure out what ratio of offspring is correct there and determine what the genotype of the offspring are. So let's erase this. Okay, so question 18 is albinism a recessive gene and what mutation is a dominant allele? Okay. Same as usual, just filling out the genotypes to get everything straightened out. So 2 normal parents have an albino child. Okay. Determine the probability that the next child will be albino. So that, so we have 2 normal parents, and we got an albino child from that. So both parents must be heterozygotes, or carriers. Let's do the Punnett square. Whoops. So it looks like there's a 25% chance of being albino. It's pretty straightforward. Okay, so now we're looking at color blindness. So color blindness is also X-linked recessive. It's important to know, and that's in the first few pages of this packet. So a man with normal color vision, so we know he is X, uppercase A, Y, marries a colorblind woman. So she has 2 recessive alleles, so she's homozygous recessive. What proportion of the children do we expect to be colorblind? So let's do the cross. Okay, so it looks like 100% of the males, so all males are going to have it. And then 0% females. That's because they get one dominant allele from their father, which is protecting them. And it looks like that answers all those questions. So that's just straightforward X-linked cross there. Okay, so a woman with normal color vision whose father was colorblind marries a man with normal vision. Okay. So her father was colorblind. So that means X lowercase a y. So that means she at least got one recessive allele there. So X lowercase, whoops, it's getting messy. So the female had at least one lowercase a allele. And because she's normal, she must have a dominant allele as well. So that is the genotype of this woman right here. And then she marries a man with normal vision. So the man, since he only has one X allele, he must be X uppercase A, Y. Let's do the cross. Okay, so what's the proportion or sons that are expected to be colorblind? So 50% the sons are colorblind. It looks like daughters 0% colorblind. Okay, so that answers all 20 questions. So that was mostly off the cuff, so I didn't really prepare very much for this. So hopefully that gave you some insights into my thinking behind the questions. So it's a little bit more authentic of how I do my problem solving. So hopefully that models how you go through these questions and how you approach them.